Okay, my physics friends, good morning, or whatever time of day it is. We're here to learn about electric potential energy and electric potential. But let's start with something we're familiar with, electric force and electric field. So see here a point charge, a positive point charge, a negative point charge, a dipole, and two charge plates to give us a uniform electric field. So here are four different kinds of fields we're familiar with, and when you look at the field, you see field lines. And what do the field lines tell you? They tell you about the force field surrounding the charged or the charged objects. So if I take a positive charge and put it here, and take a negative charge and put it here, what's going to happen? So we see the field lines. We know the positive charge will have a force on it in the direction of the field lines, and if it's free to move, it'll move along the direction of the field lines. A negative charge is going to move opposite the direction of the field lines. So the field lines give us a sense of the force, but first of all, remember it's not a flow, it's a static field. And a positive charge will move in the direction of the field lines, and a negative charge will move exactly opposite the direction of the field lines. And the direction of a curved line, remember, is tangent to the line. So the positive charge is going to move this way. It'll curve, yes, but it'll start out moving in this direction. And the negative charge is going to move opposite the field line. And if we take our charges and put them in a uniform field, it's very simple. It's a uniform field. The force is going to be in one direction, but the positive charge will move in the direction of the field. That we can see because it's repelled, because it's repelled by the positive plate and attracted to the negative plate, and the negative charge does the opposite. Okay, so that's just reviewing what we know about force. Now if we put these charges, let's put both of them in this field. Let's talk about their energy. So think about the energy. The positive charge, if it's released, will move in this direction. Let's see, what's the best way to do this? We'll move in this direction, and it will accelerate, and it'll gain energy. So that means that when we think about the positive charge in this position, we have to think about it having energy. Where does this kinetic energy come from? It comes from the electric potential energy stored, in this charge arrangement. I'm ignoring this charge for the moment like it's not there. Okay, and if we just look at these two charges, this charge also has energy stored because it's going to come toward the positive charge, gaining kinetic energy. But, okay, here's a convention you have to remember. Let's go back to the positive charge. So this is going to gain energy as it goes away, and these charges in relationship to each other have energy. So the logical way to think about where should I put the positive charge so it has no energy? Well, you can see the closer I put it, the more energy it has, kind of like compressing a spring. And the further I put it away, the less energy it has. So logically, if I put the charge all the way, very far away at infinity, the electric potential energy will be 0. So let me write that down. Okay, I rearranged things here, and I'm jumping around a little bit, so I hope it works. So we talked about the electric potential energy. So remember, we use U for potential energy, not PE. And U sub E means electric potential energy. And so U sub E infinity equals 0. I'll go back to that idea. That's our reference point. That's what we consider 0 energy. And I wrote down some other equations that I'll refer to as we go along. This is how to calculate the electric potential energy for 2-point charges. This is the definition of electric potential, which we'll be talking about. It's the potential energy per unit charge. Similar to the way electric field is force per unit charge. And calculating the electric potential for a single point charge, we use this equation. And then we want to remind ourselves, since energy and work are related, and the connection between force and energy is through the work equation. So work equals actually the integral sign I left out. Let me pause and put that in there. Looks kind of cheesy, but there it is. There's the integral sign. So the integral of F dot dr, the basic concept of work, remember from first semester, is a force times the displacement times the angle between the two. And so when the force is in the same direction, 0 degrees, it's a positive work. If it's in the opposite direction, like friction, does a negative work. And if it's perpendicular, no work is done. That's an important idea. So work connects force to energy, and we're going to be looking at all three of these equations. So let's go back and see what all this means in terms of electric potential energy. So let me take these and just put them over here where we can still see them. And let me take the positive charge and expand it, and then move the negative charge out of the way and put the positive charge here. So we were talking about how we know how to think about the force on this charge by the field, but how do we think about energy? Well, logically, if I push this closer, I have to do work. So it's like compressing a spring, it has more energy. If I go further away, there's less force on it, it'll have less energy. You can imagine if I put a charge here and let it go, it's going to go off and gain less kinetic energy than if I put it here. I hope you can imagine that. And so there's two ways that we have of thinking of the energy content of this charge in this situation. Now the way we would calculate that is we could use this equation, right? This charge times K divided by the separation between them would give us the energy. That comes, we'll talk about where that comes from later. So as R gets smaller, the energy gets bigger. That's what we expect. So the way in which we can think about the energy content of this charge is how much kinetic energy will I get if I release it? So if I release it, it's going to accelerate all the way to infinity. And as it gets farther and farther away, it's going to stop accelerating because the force and the acceleration go to 0. And it will have a constant kinetic energy. And that kinetic energy that it has at infinity will be equal to the energy that's stored in its location wherever I start. Okay? The other way of thinking about it is take this charge and put it off at infinity and then bring it in to this position. So as I bring it in, I'm pushing it, right? Whoops. I'm pushing it. Imagine yourself pushing. You have to push harder and harder and harder. So we have to calculate the work that we would do, to get this charge from infinity to here. So at infinity, it has no energy. That should be clear, right? I take this charge, I put it far away, it's not going to have any energy. So I do the work, I bring it in. So actually, if I use the equation, the Coulomb's law equation for force, and I do this integral, that's how I get this expression for energy. So two ways of thinking of the energy: the kinetic energy that I'll get if I release it and let it go to infinity, or the work that I would have to do to bring it in here. So that's the concept part of it. Now, if let's bring in the negative charge. Put this away, bring the negative charge in. Now clearly here, it's the opposite. Notice. If I release this, it's going to go in this direction. And the energy is getting more and more negative, so this gives me a negative energy. I have to do work to get it to infinity, right? If I'm going to get it far away where the energy is 0, I got to push it. So that leads to the fact, since the energy far away is 0, the energy of the positive charge in this field will be positive, and the energy of the negative charge in this field will be negative. And so when I calculate it, you can see that when I calculate it, I'm going to have a positive and negative charge, and I'm going to get a negative energy. And the way you should think about that negative energy is it's the amount of energy it would take for me to move this charge from this position all the way to infinity, where it has 0 energy. Okay, let me pause the video and go to another charge. So if we look now at the negative charge, everything reverses, not surprisingly. A positive charge here will have a negative energy. If we take this equation and use the two k's, one is positive, one is negative, you're going to get a negative energy. That makes sense because this charge is going to be attracted. I have to do work to push it away to get it back to 0 energy. And conversely, if I put a negative charge in here and I release it, it's going to do what the positive charge did. It's going to go off, and it takes work to bring it in here. So this has a positive energy. Does it work out? Yes, it naturally works out. If I put two negatives in this equation, I get a positive number. Let's try. Let me pause for a second. Okay, I decided to go back to the positive charge, and I'm going to take my positive charge and put it in here. And we can just, I hope you can see conceptually the energy stored in this charge, in this arrangement, gets bigger when I'm closer and weaker, approaching 0 far away. We calculate it using this equation. So the question is, if I take this charge and it moves this way, I'm getting energy. It can do work for me. To put it this way, I have to do work on it because I'm increasing its energy, like compressing a spring or a spring decompressing. Which way do I move it so that its energy doesn't change? So according to the work equation, I want to move it perpendicular to the force, right? If I move it perpendicular to the force. And so for this position, let's say it's 10 centimeters away, any place where it's 10 centimeters away, this charge will have the same energy, logically, physically, and by virtue of this equation, because the two k's the K, the Q's are the same, and if the R remains the same, 10 centimeters or whatever it is, the energy will be the same. So that leads to this idea of locations that are equal energy. And so if I go from 10 centimeters to 5 centimeters, the energy is going to double, and there'll be a circle in here, which is at twice the energy. Okay, let me move this charge out of here. So to have energy, we have to have a charge. To have force, we have to have a charge. But with no charge here, we still have a field, right? So the field is like a potential for a force. If I bring a charge in here, it's going to have a force depending on the field. We know the force is stronger, it gets weaker. We know the direction by the field. So the same way, in order to have energy, I have to bring a charge in here. But there's an energy field, the potential for energy, and those are rings, right? We said the places of equal energy are rings forming around these radial lines, which are perpendicular to the lines. So those rings are equal energy rings, or what we want to talk about is the energy per unit charge at any location. So if I bring a charge in here, if I bring this charge in 10 centimeters away, and I calculate the energy using this equation, but I want to know, well, how much energy do I get at this point? Well, it depends on how much charge. If I move in a bigger charge, I'll have more energy. So we want to label this point. We're going to take the charge away and say how much energy per unit charge do we have at this point? And that's what we call the electric potential, the amount of energy per unit charge. So it's just like similar to the idea of field, force per unit charge. This is energy per unit charge. So even if there's no charge, here, there's no energy, but there's the potential for energy. And that's what we call electric potential. And when we divide the energy by the charge, we get the electric potential. And if we want to calculate it, it logically comes out of this equation. If I divide by the Q2, the charge that I bring in to have energy, then we get, this equation for a point charge. So these rings around this, if there's a charge there, it's energy. If there's no charge, it's electric potential lines. And since this is energy per unit charge, the units are going to end up being joules per coulomb, and a joule for energy per coulomb is a volt. So those are volts. Let me pause the video and construct some of those lines. Okay, so I picked, I started here, and then I visually tried to double the distance. So if I double the distance, the electric potential, or the electric potential energy, right? If I, gotta get this. I can't get it. I'll just move this. If I put the charge there, it's going to have twice as much energy than if the charge is there, and that will have twice as much more energy. So just get this. I can't. There we go. Get that out of the way. So, but we're talking about potential, so we don't need a charge there, right? If I know this is 4 volts, and I bring in a 1 coulomb charge, there'll be 4 joules. If this is a 2 coulomb charge, it'll be 8 joules, because the energy, well, you don't see that, but if you take this equation and rewrite it, the energy will be the charge times the voltage. Let me include that equation. That's important. It's just a rewrite of this equation, but it's something that you'll use quite a bit. Okay, so this equation is just a rewrite of that equation, but we often know the voltage, and that way, no matter what charge we bring in, we can calculate the energy. And notice that if I bring in a positive charge, I'll get a positive energy. And if I bring in a negative charge, when I multiply by negative charge, I'll get a negative energy. Okay, let me do something else now. Okay, so notice that I brought in the negative charge, and I drew some circles, which are pretty bad. But the negative charge is going to have negative voltages. So we do have negative energies and negative voltages, and that would come out of this equation for the voltage. You see, if the charge is negative, the voltage is going to be negative. Now, in the case of the dipole, notice the way that we calculate potential, and we're just going to calculate the potential, we won't bring a charge in, is this. And so we saw over here that a positive charge has positive energies and a negative charge has negative energies or negative potentials. And so if we want to get the potential due to 2-point charges, we use this twice, no surprise. And it turns out then that in the middle, between the two charges, the two potentials cancel. And since potential is a scalar, not a vector, right? If I go up here at this point, I'm the same distance from two equal and opposite charges, and when I add the two potentials at this point, there's 0. So there's a line here of 0 potential. And so let me draw some potential lines in on this. So the equipotential lines for this arrangement, and remember what an equipotential lines means. It means a charge placed here will have the same energy anywhere on this surface. And so a charge placed here will have 0 energy anywhere along the surface. And there's a physical way of understanding that. If I put a charge here, right in the middle, there will in fact be a force on it. Notice that the positive charge is repelling it, the negative charge is attracting it. There is a force on this charge in this direction. But if I move the charge perpendicular to the force, whoops, let me get the charge. If I move the charge perpendicular to the force, that means I'm moving it perpendicular to the field lines. Anywhere along this line, I can move it from this point all the way off to infinity, and it has no energy. Whereas if I push it this way, it has a positive energy. I just randomly picked 2 volts. And if I let it go this way, it's going to have less energy, so that's a negative 2 volts. And remember, if I want to get the energy of this charge at 2 volts, I simply use this equation. Okay, the last thing to discuss is our charged plates. And this is drawn so it's 3-dimensional, and you can see that the field lines go from positive to negative. They're uniformly distributed. And so if I take a positive charge and put it in this field, that I'll have to do work to put the charge here. If it's here and I release it, it's going to go across, gaining energy. So the positive plate is going to be at a high potential, and the negative plate at a low potential. And if you remember from lab, We called the negative plate 0. We were hooked up to a 6-volt battery, so there's 6 volts. And since the field is uniform, the energy or the potential is going to drop uniformly. And so there would be a series of surfaces, three-dimensional surfaces that are equal potential, equally spaced. We did this in lab. If this is 6 volts, there'd be a 5 volt, a 4 volt, a 3 volt, a 2 volt, a 1 volt, and this would be 0 volts. So visualize plates or surfaces, flat surfaces of equal potential, equally spaced between in this charge arrangement. Okay, this ended up being an awfully long-winded video. If you lasted through it and didn't fall asleep, I hope you got something out of it. I think what I need to do is make a video where we actually do some problem solving. And it may be that after you've done some exercises and so on, if you come back and look at this, it may actually be more benefit than just watching it in the beginning. But you can let me know what you think. Goodbye.